Okay, good morning again. So, I'm trying to use the whiteboard to writing, but I don't know how it works. Hopefully you will see now, so we can write something here. We try to write something here, but let's try to see how it works. For example, x squared is equal x plus 1. So not bad, okay. All right, so if you need to write something, I will use this possibility. So if there is a sharing option here, you can also write something to me. All right. So we started for the chapter 4. Chapter 4 is only about the main sequence stars, about hydrogen burning process and how we can estimate the age from the time scale of hydrogen burning. And there is an important section of the chapter will talk about the scaling or scaling technique to study the stellar evolution coefficients. And all right. And this chapter is a bit hard because there are many different concepts and many different mathematical steps which we need to go slowly through this chapter. So I'm not in the hurry, and also you. So instead of finishing the chapter in 2 lectures, I think we will stop here 3 lectures. Or what time we need? I want to ask you about a minor change in presenting the lectures. One change is that I will use this whiteboard sometimes to write something if I need to explain more. And then I want, we will stop in each slide around 1 or 2 minutes before I start to talk. And I would like to ask you, you read it just as a first reading, and then I randomly will ask some of you about what is about this slide just. And this dialogue will take maybe 2 or 3 minutes just finally, and each slide will take maybe, not all the slide of course, will take 5 minutes. So then I think it will help more to follow the lecture, because if you just if I just show you this slide and I read it the text, or I explain it the text by my word, that will be little boring. So, and I see that maybe some of you even just connected and go. I don't know, do you hear my voice clearly, or what is the problem? Because I'm talking normally like every time. So one student write me that you cannot hear my voice. You still have a problem for that, or this is a global problem for all of you, or just a connection problem for one of you? Okay, so let's go to the. So this is the first slide I want to show you, and we will stop in this slide probably just 2 minutes to read it. All right, start it, you read for yourself, then I raise a question to anybody of you, maybe randomly just. So you have 1 minute, less than a minute. So so anybody want to talk about this slide, and what is about this slide? So I can raise the question that when the star will turn to the red giant. If the star want to turn to the red giant, so this is about the hydrogen. Actually, it's all is about the hydrogen burning. So you have a core here, so the core is filled by the hydrogen, and this is a burning process. So burning process is important for the stars in the main sequence in 2 ways. One is when the star is burning in the lifetime of the star, and the second is that when it's cooled down and turned to red giant. The things which we want to study today is the time, the average time of the average time of the burning period of the star. When the star is burning, we are going to see that how long it will take this burning process for a normal typical star in the main sequence stars. All right, so this is all about the hydrogen burning time scale. So I would like you stop here and have a look in this slide, and then I will talk about the slide for you. We talked before about the lifetime of the proton, because Star formation started by the proton-proton nuclear fusion reactions. Any nuclear fusion reaction started by proton-proton nuclear fusion. And we estimated that if you have a proton-proton, if you don't hear my voice or any problem, just turn on your microphone and tell me, because I cannot use the Google as long as I'm trying to write it, okay? So we know that in the process of the proton-proton exchange, so that was the important process as a nuclear fusion reactions. This was the fusion reactions. Fusion reactions was the starting one of the starting levels of the star formation process. We calculated the time for that. It was not easy, but we calculated the time for the proton-proton reaction. The lifetime of that is like 5 billion year actually. Now we are talking about the lifetime for this is the nuclear lifetime. So the nuclear lifetime is given by the nuclear physics considerations, if you remember. So today we are going to talk about the lifetime of stellar lifetime. So when the burning of the hydrogen will stop, how long it will take to stop that? Star, it's in the fusion, it do fusion reactions to actually to pay back the energy which it lost during the radiations. So during the radiations, so radiations send the energy in the terms of the quanta of the energy. So you have a quanta or the photon which we showed by gamma ray. Actually, the gamma ray emitted the energy from any object with thermal temperature or with the thermal convection temperature. So fusion reaction actually trying to pay back the amount of the energy which we spend or when the star or use it send it the radiations. As you see, because the radiation is related to the light, and the light is emitted from the star is calculated by the luminosity. So you can say that the nuclear lifetimes, time for the nuclear fusions is, as you see, tau is given by the energy which radiated or created during the fusion over the luminosity. So you see that it seems that you can see that from here that luminosity actually is like, it's not exactly, it's like energy per this lifetime time. So energy per time, you know, it was called power in physics. So you can remember that the luminosity looks like a power, the normal power of any mechanical systems. So if you know the energy of the fusion, you can calculate the lifetime by dividing the energy to the luminosity factors. Now we go to the next slide, and you feel free to read it a few minutes, and then I will again write it something here for you. All right. How much foil you need to for the hydrogen burning? So the foil which you need is proportional to the mass. Why? Because it's about the energy. So according to the general special relativity, so the energy can be produced during any nuclear reactions if you just you have a mass difference in your system. So if you have a mass difference, so this mass difference make energy productions, as you see from this equation. So the amount of the burning foil, this is the foil, so is depend to the mass, is proportional to the mass. And you know that from the Hertzsprung-Russell diagrams, or from the consideration of the first chapter, that for high mass star, the luminosity is scaled with m cubics. So luminosity actually for the for high mass, so for the one which their mass is really bigger than the mass of any star in the solar mass, like in the 100 times of the solar mass, the luminosity is proportional to the cubic of the m. So cubic of m means that this is the one which we know from the observations. So for lower mass, from the observation, they estimated for lower mass. So this is for higher mass. For lower mass, for low mass stars. So we know that this will be proportional to the something like 3.5. So it means that if the star is more massive, so then it will spend energy with this proportionality with m cubic, and for lower mass it will be give the luminosity with this proportionality of m power 3.5. So to get the answer for hydrogen burning lifetime, we can say that the lifetime, which is proportional to the energy, actually, you remember the previous slide, that lifetime was proportional to the energy. So, and as you see here, lifetime was proportional to the energy. So lifetime was proportional to the energy, and energy is, according to special relativity, is proportional to the foil, actually, foil supply. So, or the difference of the mass. So the better estimation for the tau will be something like m, because E is proportional to the energy, m power minus 2 to minus 2.5. How we calculate that? To estimate the lifetime, you think about that, how the mass is changed during the time. So if this is the initial mass, of the systems, so you have a radiation of that. Radiation is quantized is given by the luminosity, and I explained that the luminosity is proportional to the either m cubic, or it can be proportional to the not 3.5. All right. Now, how I can calculate the tau? To calculate the tau, I say that tau actually is like a change, is like the initial mass plus the rate of the change of the mass. Or how much the mass is changed to the radiation, so rate. You know this equation several places in physics. The m dot, the change in the mass, is always given by the dm over the time. Time here we show by tau. So if you started by the initial, this is the initial mass, this is the initial or total mass of this star. By luminosity, the star lost some radiations. Luminosity is proportional to m dot, actually. And m dot, we say that is proportional to the m cubic for high mass or m 3.5 for lower mass. Then you can say that the tau will be given by two expressions actually for high mass when m is very high in the main sequence stars. If mass is very higher than the mass of the solar system or sun, it will be m over m cubic, yes? M over m cubic, so it is proportional, or because there are some constant here, so it will give you m power minus 2. And if for lower mass, I mean if m is lower than that, very low than that, or in the range of the m solar system, so it will be m power m 3.5. This m cubic and m 3.5 comes from the observation, so it's given by the m minus 2.5. All right. So now we understand what is going in this slide. So the lifetime, the lifetime, nuclear lifetime for the high mass and for low mass stars is as the following, which we calculated. So I can show you something very interesting. So if I think that this as a m, and if I think that this is a lifetime of the star, for low mass, it will be m power minus 2. This is m power minus 2. This is for high mass, yes? When high, I write high here. You understand that this is for high mass stars. But for low mass, it is also close to that, and it's also decreasing. So it is decreasing, but instead of the m power minus 2, it is decreasing like m power minus 2.5. So from the point of the view of the lifetime, nuclear lifetime, it is difficult to make a distinguish between the high mass and the lower mass stars. Both of them are decaying, so you have a decay. Decay means they are decreasing. Decay. All right. Hydrogen burning is very important for evolution of stars, and because we will find in chapter 5 more about the helium burning. So helium, you know, all the star energy production is the base of the hydrogen to helium cycle. So you can say that the hydrogen burning it's happened at that time, and it's scaled like what you see here. All right. So why we need the hydrogen burning lifetime? Because from that, I want to calculate the time that one star can turn to the red giants, and I want to know that how much time we need to, how much time it needs to foil be finished and the star will be cold, and when the star be cold, it will be throw down to the red giant. So this is the Hertz-Russell. It's not the best, it's not correctly, but you know that here we have luminosity. So we have here luminosity, and here we had a temperature, as you remember. Okay. All right. You know that the low mass stars, it was something here we call a dwarf. So dwarf star were there. So it was a main sequence star. So here somewhere here was the sun, our sun, and the other stars lower mass. So this is the low mass stars. Low. And here are high mass stars. Yes. The one with 100 times of the mass of the sun. High. And here is our sun. So this is we call it solar system. And here is red giant region. Yeah, it is a red giant region. So the things which I want to know in this chapter is that based on the calculations which we are going to do, is that how much time one star in the main sequence needs to drop to the red giant or to change to the red giant. I want to calculate this tau. And this tau is dependent to the hydrogen burning lifetime, because when the star spend all of its hydrogen foil, so it will cool down, and by cool down, it get a chance to be red giant. Estimating so we want to estimate the age, the time from the hydrogen burning time scale. So there are actually two types of the measurements. So you can measure two things in the one is the time for the nuclear reactions, for example. So lifetime is, which we call it by tau, for example, half, is a lifetime. Is in the physics is very important. So this is actually given if you have any quantity which is changed by the time, like the mass, like the number of nuclei in the any reactions, and you have the initial mass of that. So the lifetime, or half, is a tau of half, is the time when this mass reached the half of its initial time. For example, that is the graph for some beta decay or any other decay process. So this started by some initial. Sorry, this is better to plot it down. This is, for example, think about one of these nuclear reactions which happen inside the star, like beta decay, for example, or any other, or any type of the radiation. If the number of nuclei at any time is m, so this such process started by some initial mass, and they decay. So decay means that they have a decay rate which is given by the number of the nucleoid which lost in the system, and the number of the nucleoid started from some initial, and finally, theoretically, it will be disappear fully when the time is past very long. Never happen, actually. What we call it lifetime is the time when when the number of the nucleus reach the half of the initial value. So if the initial value is m naught, so m naught over 2 will be the half time. So this is easy actually, not in the astrophysics, in nuclear physics, in atomic physics is easy also to measure that. You have a nucleus, so just waiting for the, and by using, for example, you have a neutron source, for example, in nuclear lab, and just by using the Geiger-Müller counter, you can count the number of the neutrons or nucleons they radiated or betas. So, and making a table, by making a table like here, you write the time which passed, and here, of course, it is need the calibrations and those things I don't want to say. So just reported for me the number of nucleons, the number of the nucleus, or you can multiply that to some factor and give the name. When it reach the half of the initial value, so this is the initial value, for example, at the time is 0, for example, 0 is the starting counting process. So you have M0, then it will be continue, and just by looking at the time when the number of nucleons or the mass will have, so you can read the lifetime. This is, you can read it easily, also in astrophysics. So this is a radiative decay age or radiative decay. This is, you can read it, but you need, for that, you need some information about the nuclear decay if it happen inside the stars. Yeah. So also you need the evolutionary time. For a star, estimating the radiation or the nuclear decay lifetime is not enough. Also, you need the evolutionary time. Evolutionary time is the one which I show you in the previous slide. So you need also to have a history of the mass. So, for example, you make a model for the mass of some stars, and I don't know, it goes like that. For example, in one side you have a time, in other side you have a mass as a function of time. But how know that, how to find these equations, or how to plot this graph? It is difficult because it needs a theoretical models, and very good model actually. But anyway, at each time during the lifetime of this star, you can read the mass. You can read the mass. So actually, you can tell me that exactly at what time, for example, the mass will be like here, for example, which is the mass which, for example, we need for the red giant, for example. Red, yeah. But you have to know the model. So if you have the real model, so then you can estimate this and give me the time which you needed for the star to spend all its hydrogen foil and turns to the red giant. But we don't have this very easily, so it needs a lot of modeling. So what we do to assigning the age for the star is that we are mixing the hydrogen burning lifetime with evolutionary process. All right. Combination of all of them. The evolutionary method is, what is the evolutionary method? The evolutionary method is giving the estimation what, as I mentioned here, for the mass of the object during process. So evolutionary technique is have some step. So first we need hydrogen burning lifetime. This depends to the mass, as you see. So if you have the mass of the main sequence star, and which you can estimate it from the luminosity and temperature, but you can tell me that the mass, where is the mass? So from the Hertzsprung-Russell diagrams, you can tell me that in which luminosity the star has which temperature, or in which range of temperature, what is the estimation of luminosity. And then you can estimate the mass of that object and the location of the star. You can see that this is, you remember the Hertzsprung-Russell diagram, which I show you that here. It's not the best one, but it's just by hand. But you cannot, from that, you cannot say actually how long ago it formed. I mean, the age of the star, you cannot estimate it easily from Hertzsprung-Russell. To know the age, you have to know that what was the initial mass, yes, and how many process happened here, which the star finally drop and reach the mass of the M with this specific luminosity and temperature. So you needed the process. So the process which you needed here, all the detail, I mean, you need the detail to tell me the age of that. For the star to reach this luminosity and this spatial mass, we need to know the age. And age, you cannot estimate the age from Hertzsprung-Russell diagram very clearly or very easily. You cannot do that. What you can say is that just when the star jump to the red giant regions, it means that the burning period is past. So from here to here, I can say that if I have a main sequence star, just when it will turn to red giant, when the hydrogen foil is finished, actually burned completely. This is what I can say on. But you can just, and by this information, maybe you can say that from its mass, that how long that takes. So again, I want to say that if you go to this Hertzsprung-Russell diagram I plot for you here, so if you can estimate it, if you want to tell me that how much tau, so you can say that this is when the star turns to here, when the hydrogen burning process is finished. And if you know the mass here, so then you can say that how much time you need to be red giant. All right. This is what you can do. So you can assign an age for the star just when they leave the main sequence. This is called main sequence turn off, or MS turn off. So when the star is leaving the main sequence, then you can estimate the time, that how much time it needs to be red giant. In Hertzsprung-Russell diagrams, a group of the stars actually are collected and formed according to the same structure of the gaseous structure. So it's about that from which material the stars are made. Actually, the age of the star at main sequence actually gives you the age of the whole cluster. So this is called cluster dating or cluster age. So cluster dating is very important because this is the only way we can estimate the age of stellar evolutions. So you understood that the Hertzsprung-Russell diagram is statistical diagrams. So it's for the cluster of the stars, and if you can estimate it, the turn-off time or main sequence turn-off time. So then it's not for one, it's for the clusters. So again, I want to drop this not very good form of the Hertzsprung-Russell diagrams. So here are the red giants. So this is the red giant. So you understood that if you have the mass of the stars here, which we have, because we have the temperature and we have a luminosity, so you can exactly tell me that what is the mass of this. And they are clusters, so they have, it's not one actually, they are a cluster, so a collection of stars have the same mass, like M92, for example. M92, for example, is the name of one of the clusters in the main sequence, which they have almost the same mass. So if you know this mass, then you can estimate the age with assigning for this cluster to turns to the red giant. So this is called MS turn off. MS turn off was the time which you need for a cluster in main sequence to leave the main sequence and to turns to the red giant. Okay, I want to raise a question here. You know the estimation of the time for the PP fusion reaction. So can you tell me that what you estimated, how billion or million years will be the time for the main sequence turn off? For example, our sun is here. Sun will be finally a red giant when it's burned all of its hydrogen. It took the time of the MS turn off. So MS turn off, main sequence turn off, is the time which it needs to turn off. Okay, is the time which a star like a sun needs to spend to drop to the red giant family. How much time will be that? Should be worry about the main sequence turn off time scale. Should be worry about that. I mean, it will affect our life as long as we are alive or not. This is the Hertzsprung-Russell diagram, but this is actually the real Hertzsprung-Russell diagrams, which we use the absolute magnitude M instead of the luminosity, and the horizontal axis is also BV. So main sequence turn off age are the time which such clusters like M67 or Comma or Pleiades or NGC 2362 will turn to the red giant. This is the red giant region. And this is the main sequence this time. We can, if you go to the experimental for the one special cluster, which, for example, all the global cluster M92. So and if you compare that with theoretical Hertzsprung-Russell diagrams for the same age, you can get around the MS turn off is around 40 billion years for this cluster, M92. All right. So for one cluster, for example, M92, M92, it will be 40 billion actually. For the PP chain reactions, so the time is 5, so it will be longer. So it will be longer than the lifetime for the fusion PP reactions. Okay, this section is about the rescaling. So I want to summarize what I say so far. So because the new subject is completely different from this, is about the scaling of the equations. All right, okay, I want to raise a question to Maha Al-Amri. So, what was the lecture today about? Generally, just in one few words, tell us what was the lecture and what we're trying to calculate. Are you here? Or?
Yes, yeah. I am here.
Just few words about what we discussed and what we show today.
It was about burning hydrogen and how we calculate lifetime.
So we talk about, yes, the time which one star needs to leave the main sequence, and be red giant. All right. And it was a lot of consideration and assumptions, actually. Okay, anybody else, like, for example, Shafa, so Shafa al-Rashidi. You can tell me that, Shafa, that what is the dependence of the luminosity to the mass for high mass and low mass stars on the main sequence? Do you remember this? The luminosity depends on the mass, as you know, because it depends to energy. So can you tell me for high mass stars how it changes? M square, M cubic, M4, M5, how it changes the luminosity? So it changed like that, huh? We show that we say that from observation for high mass star, luminosity change as a cubic. For low mass, it changed like M power 3.5. Okay. The rest of the lecture is about scaling. So what is scaling? Okay. What is scaling? So scaling of a structure, stellar structure equation. You remember the equations which we have? We have the equation for the gas, equation of the mass balance, equation of luminosity or radiations, hydrostatic equilibrium equations, and which needs a gravitational energy. So we have 4 or 5 equations along the equation for the gas. What is the rescaling? So we say that the stars in the main sequence have the same properties, and they are actually sit in the clusters. So clusters are a group of the stars. So when you set some stars in one group or cluster, you expected some properties of those clusters remain the same, even when the member of this cluster have some different parameters. Scaling help us actually to see that what happened in stellar equations when the change in a star happen and when it goes to the red giant branch. Actually, we want to know that the change which happen in the chemical compositions when the star leave the main sequence, this is because of the conversion of the hydrogen to the helium. So we need to use the one principle to know the change which has happened to stellar evolutions when they move from main sequence to red giants. This principle is, first of all, what is the question? The question is that how we can use a simple analysis of the stellar evolution equations to find approximated equations for luminosity mass of the main sequence star. And we want to know that how the luminosity, radius, and temperature of the star will change when the mass of this or when the chemical energy is changing. These relations actually can be obtained using a principle called homology. Homology is like the scaling symmetry for the equation. So we make a scaling change in the one or two of the parameter, and then we want to see that how the final equation will change after this scaling symmetry. So in other words, it means that when the star undergoes the change in luminosity, density, or temperatures, structure in the sum factors, for example, when the luminosity becomes double, density becomes triple, or temperature becomes 1,000 times higher. So we want to know that the structure, how it will change. I mean, the chemical potential, for example, how it change, or mass, how it change. Because why we need? Because I told you in main sequence, the star are clusters, and clusters, they have a similar range of the temperature and luminosity, same luminosity, but they are not. They don't have exactly the same. So, for example, if the luminosity change by the factor of A, then the luminosity everywhere will change by the same factor. So what does it mean? So for example, this is the star, and we know exactly, we know exactly this is one star, and we know by somehow, we can estimate it, the mass radius equation for that. It comes from the stellar evolution equations, and you can tell me exactly the luminosity at the surface of the star. You know that the surface of the star, it doesn't exist actually like a solid. So it was like a cloudy actually of the gases particles. So this is the surface. If you know for the surface how the luminosities change. Now the question, what is the question? I want to, you have a cluster, so their luminosity is scaled differently. I want to know that if the luminosity the surface at R, change it by a factor of A, for example. Then this factor A also will change the luminosity at the intermediate radius. I mean, not only the luminosity in the surface will change, at any other distances. This is homology actually principle. Say that if the boundary actually change, so then the luminosity will be changed for each point of that with the same factor. Okay, if the surface becomes 100 times more luminous, then the luminosity inside the star also before the surface will be also changing. So, or from the other side, if the temperatures of the core, for example, again we say this is the star, for example, and this is the core. So core is the source, actually, remember for all this burning hydrogen. If the temperature at the core, Tsc, if Tsc is a constant, if Tsc just changed by the factor of B times of the previous value of that, then the homology principle say that, okay, this scaling change will also change the temperature at any other point, not at the center, at any other point by the same factor. So TR will be changed also by the same factor, not only for the center, for any other point inside the star. This is called homology principle. Then we can also, you can say about the density and pressures profile. If they change by factor of C or D, then we can say that this change in the factor will be translated to the pressure and density of any other point, not only the center. So it seems that you have a scaling symmetry here, like that. You have a scaling, so this homology principle is very important physical. So it gives you actually something like gives you some idea about the scaling difference, not only in the spatial surface or center of the star, but also about any other internal point. So also, if we have, so we assume that we have the star. What is the main assumption? The main assumption in this calculation of homology principle is that we have a star. The star have a mass of m and the radius of r, and this is the r is the radius surface actually at that, and we have a luminosity for the star, and there is a chemical potentials which is related to the mass actually. This is a mean molecule mass actually, mean molecule mass. So mean molecule molecule mass. So we can say MMM, mean molecule mass, molecule mass. So this is the molecule mass average. So actually M mu, we can call by mu. This is the star we have, and at the core, this is the core. We have a pressure at the core and center density at the core. So, and pressure at the surface is 0. This is the condition for the star. Star will get the radius when the pressure is 0, finally reach the 0. And you can not only talk about those parameters, you can talk about the average density for the star. So this is in our context, we have this information for this. Always, if for example, you remember, if I give you this, if I give you this as a, if I give you this as a pressure versus the radius for the star, so at the center, so pressure will be we call it PSC at the center. Then it will be changed, actually, it will be changed, and finally somewhere it will be 0, because after that you have exterior regions. I mean, this is the interior region, so this is the interior, so this is a interior actually. And this is the exterior region. Exactly here, when the pressure is 0, you can say that this is the radius of a star. How this equation comes? It can come from different model like that even. We don't know that exact model here, so because it needs the stellar revolution equations. You know, we have in the stellar revolution equation, we have dApdr actually. We have dApdr. It comes like a function of minus gm. For example, you can see it in the other slide, gm. M is a function of the r, is the mass of the star at the spatial radius, over r square. So, you know, this is very complicated differential equation because you don't know the mass here, the mass profile. And there is another equation which gives you the dm actually. So m actually at the distance of r, you remember m at the distance of r was proportional to the integral of density actually. Proportional to the integral of density as a function of r, which we call it r prime because here, and the volume here, dv prime, is the volume of the star from 0 to r. Of course, there is a 4 pi here. You can write it. So there is no, there is nothing here because I write in the volume form. If you write in the volume, so there is nothing here. All right. This is what we want to say. So I will stop it here. So then this is the one I call it about the cluster. So this is an example of cluster: Young cluster, old cluster, and global cluster. So for each one, you can calculate the age of them. For example, for old cluster, the age is 100 million years. For younger cluster, this is a younger clusters, 100 million. M67, so this is the B, is the oldest open cluster. So you see that this is a closed cluster. So this is very open cluster. I mean, you know what is this? The scattering of the stars here are more. They are more scattered. And this is the other global clusters with the age of the 14 billion years. All right, I will stop it here, and then later we go to the detail of the mathematical detail. All right. I hope you find this interesting and useful. I will stop at the sharing, and I stop at also the video recording. So